right, everyone, let's see what we can figure out on this practice exam. All right, so the first question, this is what I would consider like a definition type question, just looking at all these different definitions and seeing if they match. So when is a system in equilibrium? If the number of grams of reactant equals the number of grams of product, no, right? It doesn't have to be equal of those. The rate of the forward reaction is equal to the rate of the reverse reaction. That sounds good. The reactant has all become product. Absolutely not, right? Equilibrium means that there is some reactant left. And the number of moles are equal. No. So the only one that makes sense is B. All right, write a balanced reaction for this. Okay, so we've got, this is our product, and there should be two of them. So we're looking for BRF3, two BRF3s. And then we want F2, three of those for our reactant, and BR2 as a reactant, so B. All right, for the reaction X plus Y is Z, the reaction rate is found to depend only upon the concentration of X. Plot of one. Okay, so remember there were three different graphs we could make. Versus time, we could just do concentration. We could do natural log of concentration, and we could do 1 over the concentration. And each of those corresponded to a different order of reaction. If the X, the concentration one, was straight, then it would be 0th. If the natural log was straight, it would be first. And if 1 over was straight, it would be second. So this is a second order reaction. Only depends on X. So that looks like we're on a roll with B's here. All right. Which intermolecular forces would you expect? Okay, so this looks like a polar molecule to me. I'm saying that because, by the way, the notation of this, these are all carbons at the corners and there's hydrogens here. But what I see is that there's some opposite stuff away from, like opposite from each other that would not cancel. So it looks like it's polar. So yes, dispersion 100%, right? We know that. Dipole because it's polar. And then here we have a hydrogen directly bonded to an NO or F, so it would have hydrogen bonding as well, so E. All right, sulfuryl chloride decomposes at a high temperature, blah, blah, blah. The rate constant is this. What is the order of the reaction? So they don't give me any information except for the rate constant, so how will I decide? And the answer is I will look at the units of the rate constant. If I only have inverse seconds, that is a first order. If you weren't sure, what you could do is you could write like essentially this, right? This is be my reaction. Solve for K. So K would equal rate over concentration, like some concentration. And rate would be molarity per second. So what I need in the bottom to cancel out the molarity would just be 1 molarity. So it would be first order. That's kind of the thought process I'm going through. All right, dissolving a solute such as KOH in solvent and water. Okay, so this is, I look at my choices, I see they're all about colligative properties. Remember, any solute is going to make the boiling point go up, the freezing point go down, and the vapor pressure go down. So no change in boiling point, nope. Decrease in boiling point, no. Increase in melting point, remember that's the same as freezing point, so no. Decrease in the vapor pressure, yes. Solubility of gases in water, okay, so decreasing. So for gases, I'm going to think about it increasing. I can increase the solubility of gases if I increase the partial pressure or decrease the temperature. So this is asking the opposite. This is saying the solubility decreases. So either if the pressure decreases, I don't see that choice, or if the temperature increases. And again, so I wrote it kind of backwards here. I wrote how I'd increase solubility because that's what I know. That's kind of how I think about it. But then I can draw the opposite. I can draw the same conclusions. All right, which of the following aqueous solutions has the highest boiling point? It tells me what the Kb is. They're all the same concentration. Remember, boiling point goes up. So the more concentration, the higher the concentration, the higher the boiling point, and that's the same. So instead, I need to think about I for each one. So aluminum hydroxide would separate into 1 aluminum, 3 hydroxide, so that would be a total of 4 particles. KCl would be 1 potassium and 2 chlorines, a total of 2 particles. Sodium sulfate would separate into 2 sodiums and 1 sulfate, a total of 3 particles. So the highest boiling point would be A. Which of the following would you expect to have the highest boiling point? Okay, this one's not solutions. This is just stuff. So I would look for, are any of them polar? So this one is not polar. CH4, remember carbon-hydrogen bonds are not polar. pH3, that would be like this, which would be trigonal pyramidal. That would be polar. NH3 would be exactly the same if I look at my periodic table, which I don't have one handy, but they're right on top of each other, so they would have the same type of geometry, so that would also be polar. So I can narrow it down to one of those. Then I can look for hydrogen bonding, and NH3 has that, so that would have all 3 intermolecular forces. And then finally, which of these is cubic? So remember, simple cubic is 1 atom per unit cell. It's just the corners, the 8 corners, and 1/8 of each one. Body-centered cubic is that plus 1 in the middle. And then face-centered cubic is, is the 4. It's the one coming from the 4 corner, or the 8 corners, the 8/8 plus 6 faces, each one half in, half out. So that's a total of 3 for a grand total of 4. And that's my answer then. All right, so writing equilibrium constants, remember I just do, so this would be a K, products on top, raised to the stoichiometric coefficients, reactants on the bottom. If there are solids, they do not get included, only gas and aqueous. So for this one, I have chromium 2 plus on top, squared, cadmium 2 plus, and then chromium 3 plus, squared. And then the cadmium is just not there. All right, we've got a Le Chatelier's principle question. All right, so it says, how will each of the following affect an equilibrium mixture? What if N2O4 is added? I see N24 right here, it's a reactant, so if I have too much reactant, it will shift it to the right to make more product. If the volume of the container is cut in half, so this is giving it less space. Remember, this could also be increase the pressure. That would be the same effect. So decrease the volume and increase the pressure would both do this. If I'm giving it less space, it would shift to the side with less gas. Or less moles of gas, I guess I should say. So when I look at this, I have 1 mole of gas on the left, 2 moles of gas on the right. So it's going to shift to the less moles of gas, shift left. The reaction is heated. I do need to know something about the delta H in order to answer this question. This is a positive delta H. That means it's endothermic. So I'm going to write the word heat over here on the left. If I increase the heat, then it would shift to the right. And then finally, NO2, a product is removed, so that will make not enough product, so it will shift to make more to the right. All right, here we have an equilibrium problem. They're asking me for the Kc, that's my question. I'm given my starting stuff and also some equilibrium stuff. So that means I need an ice table. If there is anything where it's like, this is what's put in my solution, I need an ice table. I'm going to go ahead and write this longhand just to make it a little easier to see what I'm doing. So this is 1 times 10 to the minus third, so 0.001 and 0.002. I'm just converting those. And then this would be 0.00187, which, okay. So then my ice table is H2, I2, 2HI. I'm starting with 0.001 and 0.002. Remember, these are already in molarities, but if they weren't, I would convert them. It doesn't say I started out with any HI, so I didn't. For my change line, I'm going to have to use up some of what I have and make some of what I don't have. So I'm going to have minuses over here and plus over here. And remember, the stoichiometric coefficients come into play here. Add them up to get to the change line. And then at equilibrium, I do know one other piece of information. I know this is equal to 0.00187. So now I can figure out what x is by dividing. Now I've committed to longhand. I'm regretting it. I should have stayed in scientific notation. All right, so I'll come and plug those in over here, plug the x in over here. So this is 0.001 minus 0.000065. And then here, 0.002 minus 0.000935. Got to count my zeros. If I just did scientific notation, it would have been easier. But oh well, if you stayed that way, that's fine. All right, 0.01065. Okay. So I have real numbers for all of my concentrations at equilibrium. So I'm ready to write my equation for K. Products on top, HI squared because of the 2. H2 and I2 on the bottom. And then I just plug everything in. One, 2, 3, 4, 6, 5, and 0.001065. I'll put it in my calculator. 0.000935 squared divided by 0.1234. Oh, wait a minute. Sorry, I put the wrong number. Look, this is x. What it actually is 2x. That's not right. There we go. Try it again. All right, 50.5. That's what I was supposed to get. Whew. All right, so that is an equilibrium problem where I'm given some starting information and equilibrium information, and I'm being asked for K. All right, here we've got a kinetics problem. I'm looking for the reaction order with respect to each thing. I'm going to write my generic rate law to begin with. So this is going to be lowercase k times F2 to a power and Cl2O to a power, and I'm looking for those powers. That's the answers to A and B. So for F2, I'm going to look for reaction experiments where F2 changed, but Cl2O stayed the same, and I will use 3 and 1 for that. I like to do the one with the bigger concentration on top, so I'll say 1.0 times 10 to the minus 3 molarity per second, remember this is what I'm plugging into, equals K times 0.10 molar to the X times 0.010 molar to the Y. And then for number 1, 5 times 10 to the minus 4, 0.05 molar, and 0.010 molar to the Y. And then I divide. Okay, so that's my division line I kind of crossed. All right, anyway, you get the idea. 1 times 10 to the minus third divided by 5 times 10 to the minus fourth gives me exactly 2. Oh, exactly 2, if you can see that. And then 0.1 divided by 0.05, divide the numbers, keep the exponent, the molarity would cancel, so 0.1 divided by 0.05. And I get 2 equals 2 to the x, so x equals 1, so it is first order. All right, I'm going to do it again for Cl2O. So now I'm looking for one where that is changing, but F2 is the same, so I'll do 2 and then 1. I didn't do that right at all. Number 2. All right, 2, the F, this is 0.05, and this is 0.04. Okay, there we go. I was looking half at one, half at the other. Easy mistakes to make, so just check yourself and hopefully you'll see it like I did eventually. All right, now division bar. These cancel. 2 times 10 to the minus third divided by 5 times 10 to the minus fourth gives me exactly 4. And then this gives me also 4. So y equals 1. And so that's also first order. For the overall reaction order, remember I just add those together. This is an overall second order reaction. And that just means 2 molecules are included in the rate determining step, and one is F2 and one is Cl2O. All right, and then finally it's asking me for the rate constant, so I'm going to go back and write my rate law, but I'm going to plug in 1s now for my exponents, which basically means just get rid of them, right? And I'm going to solve for K. So divide F2 and Cl2O over to the other side. Plug in, just pick one of the experiments, and I'll choose the first one and be more careful to pick everything from the same line. So I put in the 5 times 10 to the minus fourth molarity per second, and then 0.05 molar and 0.010 molar. One of these molarities will cancel. I've got 5 times 10 to the minus 4 divided by 0.05 and divided by 0.01. And so I get 1 is the number in my calculator. When I go back and look, though, I probably, 1 or 2 sig figs. I don't know. I guess this only has 1 sig fig, so I'll just leave it at 1. And then my units would be molarity on the bottom, or I can write -1 and seconds on the bottom. All right, here is a mechanism problem. There we go. There's the word, mechanism. So here's my overall reaction. Here's my rate, or my mechanism, and it asks me for any intermediates. Remember, an intermediate is something that's made in an early step and used up in a later step. And that's all I see, so NO3. A catalyst would be something that I would put in an early step and I would get back in a later step. It would not be NO2. That just is stoichiometrically there's some involved, but they don't. So it might look like one of them cancels and only one gets used in the reaction. No, that's just not. That is a reactant. It's just you need multiple in order to get the reaction going. So I would say none. And then finally, the rate law. Remember, rate law always looks like rate equals K, and then times the reactants. This would be in the slow step. And so the slow step is NO2 plus NO2, so it would be NO2 squared. All right. We are converting between Kp and Kc. All right, so I'm given a Kc, and it's 0.083. And then I need to multiply it by R times T times delta N. So R is the gas constant, and that's the 0.0821 liters atmospheres per mole Kelvin. Remember, we want that one because we're trying to convert between molarity, basically, and atmospheres, right? And so we want the one that has moles and liters and atmospheres. And then the 900 needs to get converted to Kelvin, even though it's already a big number. And then finally, we need this delta N, which is the number of moles of gas in the product part. So that's 2 moles of gas in the products, minus the number of moles of gas in the reactant part, which is just 1. And so N, delta N equals 1. So this just gets raised to the first power. So 0.083 times 0.0 0.821 times 1173, and I get 7.99, which looks like 8.0, Kp 8.0. All right, we've got a crystal structure calculation. I should be ready to do all the different parts of this, or maybe on an exam, maybe there's not time to do all the parts, so just be ready to do whatever the question is asking. Eventually, the full question is basically like, what is the density? But I can do the parts in order to get there. So let's do the mass of the unit cell. The mass of the unit cell, I'm going to look at my periodic table, which again, I don't have one handy, but that I can pull over, but I see that the molar mass of vanadium is 50.94. That would be grams per mole. Then I use Avogadro's number to convert that to grams per atom. There are 6.022 times 10 to the 23rd atoms in 1 mole. And then I use the fact that this is body-centered cubic. Remember, that means it's 2 atoms per unit cell. And so I can put this in my calculator. And I get 1.69 times 10 to the minus 22 grams per unit cell. All right, for the volume, I want to just take the edge length and cube it. I'm already given the edge length, which is 305. Remember, if I was given the radius, I would need to convert it to edge length. You do not need to memorize the equation for radius to unit cell. For, it's different for each of the packings. I would tell you that if you needed it, but I don't need it this time because they already gave me the edge length of the unit cell, which means all I have to do is cube that. Personally, I do want to convert to centimeters first. Remember, in 100 centimeters, which is a meter, there are 1 times 10 to the 12th picometers, which is a meter. And so if I use that as my conversion factor, I can get the edge length in centimeters, 3.05 times 10 to the minus 8th. And that's centimeters. So for the volume, it would just be the edge length, which we call A cubed, so I already have that in my calculator. I can just say the whole thing to the 3rd power, and I get 2.84 times 10 to the minus 23rd centimeters cubed per unit cell. For the density then, I just do mass divided by volume. And I would get 1.69 times 10 to the minus 22 divided by my answer, 5.96 grams per centimeter cubed. All right, the molality. What molality of a non-volatile, non-electrolyte solute is needed to raise boiling point of CaMa4 by 12 point? All right, so by 12.5 degrees, that sounds like that's the delta TB. So that's what I'm looking for, or that is the number for the delta TB. Remember, that equals KB times M, and that is the question, is what is M? So let me just solve, I guess I'm going to solve this first. So M equals delta TB over KB, where delta TB is the 12.50. That's how much I want it to go up by. And the KB is given to me. .10. The degrees Celsius would cancel. Molality in the denominator of the denominator, 2.10 molal. All right, how many moles of solute would I need to add to 145 grams of chemophore to produce the solution with the molality found in part A? So molality equals moles of solute divided by kilograms of solvent. And this time moles of solute is my unknown, so I guess I'll just solve again. I'm going to cross multiply. I mean, you could kind of just use units to figure this out too, but I'm going to just do it the formal way, the fancy way. So the molality I figured out in part A was 2.10. Remember, molal means moles per kilogram, so I'll write it like that so I can see. That will help me remember that this 145 grams of chemophore, that's my solvent here, needs to be converted to kilograms. And I get 0.305. And that would just be moles of solute. All right, circle the acids in the reaction below. Remember, an acid is the thing that's going to lose a hydrogen. I can look at hydrogens and see what it's attached to. Right here, one hydrogen is attached to one chlorine. Here, the chlorine does not have any hydrogen anymore, so that sounds like an acid. Here, the oxygen is attached to one hydrogen. Here, the oxygen is attached to two, so it gained hydrogen, so that would be a base. Down here, I've got all my hydrogens are in here, and they're still kind of the same. But this oxygen, the water here, is attached to two hydrogens, and it loses one, so my water is acting as an acid. Because this one had a one-way arrow, I only needed to do reactants on the left, but since this is an equilibrium arrow, I do have both reactions happening, and I should choose an acid in the reverse reaction as well, and that would be this, right? I've got the all these hydrogens, and then there's this extra hydrogen on the end, which is lost when it goes backward. So those would be my two acids in the bottom one because it's equilibrium, only one acid for the top one since it's a one-way situation. All right, fill in the following table. All right, so I'm just gonna, just sort of talk through this as I type these into my calculator and explain what I'm doing and not write it all out. So wherever I have a pH or a pOH, I'm going to do 14 minus it to figure out the other one. So this will be 11.49 and 12.9. Then I'm going to, once I have pHs, I would do 10 to the minus of whatever I've got over here to get these. So I'm going to just do each one individually. 4.9 be 3.2 times 10 to the minus 12th. And that should technically have a unit of molarity, so I'll put that in there. And then, I could do the 1 times 10 to the minus 14th, but I'm just going to do it from this. So I'm going to do 10 to the minus 2.51 and get 3.1 times 10 to the minus 3 molarity. 10 to the minus 1.1, 10 to the minus 1.1, 7.9 times 10 to the minus 2, and 10 to the minus 12.9. 1.26 times 10 to the minus 13th, or 1.3, I guess. I was doing everything to 2 sig figs. Whatever. Okay, then for this last one, I do need to do, well, I can do a couple of things. Maybe I'll just go this way. So I'll do the pOH by doing minus the log, log, of 3.1 times 10 to the minus 10th. And I got 9.5. 14 minus that, 4.5. And then 10 to the minus 4.5. So I just got to make sure I line up my boxes. And I got 3.2. times 10 to the minus fifth. Then once I've got all of this done, that's what I would do first, and then I'd figure out the acids and bases based on just the pH. So then above 7 would be basic, and below 7 would be acidic. All right, and then finally, I have a pH of a weak base. So for the base problems, I like to just write base, but you could write the whole thing. Remember the equation for a weak base, what it's going to do. It's going to react with water to take a hydrogen and leave behind a hydroxide. So this 1.67 times 10 to the minus 2, that's my original base. That's my solution. I'm going to convert that. Water I don't care about, and my other stuff I don't have any of. It doesn't say I have any of those ions, so I don't. All right, then I do minus x plus x plus x. All right, then for my equation for K, I would put products on top. That's HB plus and OH minus divided by the base on the bottom, and water doesn't get included because it's a liquid. The Kb was given to me as 3.1 times 10 to the minus 5. HB plus and OH minus are both x, so that's x squared on top, and 0.0167 minus x on the bottom. This is where I can assume x is small. And if x is small enough, then 0.167 minus x will basically still be the same as 0.0167. Now I'll cross multiply. Sorry, I've got a lot of glare here. 0.0167. And I have 5.177 times 10 to the minus 7th. And then I take the square root of that to get 7.195 times 10 to the minus 4th. All right, I have a couple of things to do. One is that if I made an assumption that x is small, I should check if that's true. So I'm going to check my x is small assumption, which is by putting x on top and the original acid on the bottom. Multiply it by 100. There we go. Okay. All right. 0.167 times 100, so 4.3%. So that is under 5%, so we're good. Then we need to figure out, okay, it's asking us for the pH. Our x is OH minus, so we can figure out the pOH by doing minus the log of OH minus. .195. And it's 3.14. And then I can find the pH by doing 12 minus that. 8.86. I think that's, oh, wait a minute. Okay, that's not the answer, though, because it's not 12. 14! I don't know what I'm looking at, what I'm thinking here. 14 minus 3.14. My computer died in the middle of that recording, and it flustered me. All right, there we go, 10.86. And that is the end of our practice exam. I hope it helped. Good luck. See you soon.